Everyone hear me out there, and can everyone see one of these screens? Great. What about out there in chat land? Can you hear me out in chat land? Great, great, great. So I'm going to try to remember you guys that are in chat. Okay, so what I'm going to do today, because at the end of my lecture last week, I went through sort of PalMod and the CRT multiplication extremely quickly. We're going to go through it sort of again more slowly. But before we start, I need to know if there's anything you would like to clear up about any of the material that comes ahead of that. So like now that you've sort of had a chance to actually engage with the project and look at the code, either you've understood more enough to understand that something else you don't understand, or, well, I guess what I'm trying to say is now that you've done the project, you may have more questions about the project. So why don't we sort of open the floor to questions, if anyone has any. Because like this is what sort of this hour has been designated for. So, yes, sir.
The multiplication algorithm, the CRT one.
Yes.
That's for calculating in ZX or in like specific ZP.
The like this one, this multiplication.
Yeah.
It's as you see here. It's going to return. Oh, hold on. Is that a mistake? Yeah, that will return. Sorry, in ZX. That's actually wrong. Thank you for, I'll correct that. Yeah. That's going to return to you a product in ZX. Yeah.
So then for the multiplication in ZP, we need to use a different method.
You need to actually implement a multiplication mod P, right, in order to use it. Because in these CRTs, where is it? Yeah, here. You're going to have to do a multiplication in sort of Z3, then Z7, then Z11. So yeah, we'll go over this again, but the idea is you have to truly implement a multiplication algorithm for polynomials mod P, and I did give some pseudocode in these notes for doing that. Right? You just have to make sure that every time you do any type of term arithmetic, that's getting reduced. I also need to point out, someone said that the Chinese remainder actually requires polynomial arithmetic. That's not entirely true. So this is the only product that you're going to find in CRT. It's not actually a multiplication on two polynomials. Right? This is a multiplication of two terms. Right? So this is quite normal for us to be using multiplication of terms in a multiplication algorithm. So for CRT here, you only need addition in ZX and multiplication on terms of ZX, but not totally generic multiplication. Is there anything from the chat? Or because again, like if you guys don't ask questions, then I'm not going to be very, very useful. But mull on your questions. I'm going to go through the PalMod stuff again, and then the Chinese remainder stuff again, and perhaps then questions will come to mind. Oh, yes.
So just to clarify, but you still need multiplication mod P for multiplication, not mod P.
Yes. You're supposed to create multiplication mod P.
Right, and then we use that.
And then you use that for multiplication in ZX.
Right, okay.
Yeah. So the multiplication in ZX is going to be based upon your multiplication in mod P.
Yeah.
But you will have to go and create a mod P multiplication algorithm. And there is pseudocode for you to do that, right?
Yeah.
Okay, thumbs up? Yeah, this seems to be a point of confusion, right? You're improving the generic ZX multiplication by creating a ZP multiplication and then using that in the Chinese remainder. But let's go through it, and then perhaps it will make more sense, or you'll figure out what is unclear. Let's start with the Chinese remainder algorithm then. Okay, so let's recall what the Chinese remainder algorithm does. And we'll just do a simplified version where it gets two inputs. So Chinese remainder theorem, it sort of answers the question, like suppose we have some secret number, and I know the image of that secret number mod P and mod Q. Am I then able to recover the secret number? Yes, right? So that's what you're going to have to do. The first thing you're going to have to do is implement some type of integer Chinese remainder. Now this actually may exist in Julia, but I also gave you the pseudocode to actually do Chinese remainder theorem on integers. Yes, sir.
I actually have a question on that.
Yeah, so we'd really have to double check with Yanni, but I don't think it would be a problem for you. You're talking probably about calling in CRT.
Yeah, and no, I want to see both primes package because that helps a lot.
Oh, and primes, yeah, sure. So I really can't render a decision on this because I'm not the coordinator, but I would say that it's fine. You should, like, the very worst that will happen is if you're using those library routines and Yanni says you can't, you just have to go sort of write them, right? But just make it so that you can easily sort of swap it out for something that you write. Okay, so let's just go through this. If I define a polynomial like this, I'm going to define the height of the polynomial by the largest magnitude of any of its coefficients. So for instance, 2x squared minus 5, its height is 5, right? Because minus 5 is the coefficient with largest absolute value. If I further let pound a equal the number of non-zero terms of a, so for instance, the number of non-zero terms of 2x squared minus 5 is equal to 2, which you should note is going to be less than or equal to the degree. But like, it's certainly not the case that you can use degree when I want to use like sort of this hash command. Now consider that if we intend to use CRT to calculate the product, I need to tell you how many primes to use before you can stop. Right, so the reason I'm sort of defining this height and this number of non-zero terms is so I can tell you how many primes will be necessary to use in your CRT multiplication algorithm until you can stop, right? I sort of have to say, what is the prime that I would have to use to ensure that I'm going to get the same number back that if I were to do multiplication in ZX? And sort of this is why we define the height, right? So if I know this polynomial, 2x squared minus 5, if its largest number is 5, that means that I'm going to need at least, well, it's minus 5, right? So I need to go from minus 5 to at least plus 5. That's going to be accommodated by mod 13, like because of this symmetric mod. But you sort of have to ask, what is my largest coefficient, and how big does a prime have to be so that that coefficient is itself in that congruence class? Right, so if you don't really understand anything I said, like the punchline is this, right? You need to do Chinese remainder theorem until your m is in excess of 2 times the height of the product. Okay, but it's sort of backwards reasoning or circular reasoning to say, well, I don't have the product. How am I supposed to stop on this bound? Well, we can sort of estimate what the bound should be. The largest coefficient that can appear in the product of two polynomials, a and b, turns out to be bounded by this expression. So the largest coefficient that you're going to be able to find in C is bounded from above by the largest coefficient you're going to find in A times the largest coefficient you're going to find in B times the minimum number of non-zero terms among A and B. Okay, you just have to do a worst-case analysis where you multiply this A by this B, and then you just sort of ask yourself, like, what is the largest coefficient end up being in that product? And it just turns out to be this. Okay, so I put an example here where I've actually told you like what you should get at every step of your algorithm, right? So this is a great example for actually debugging your code. So this is the idea, right? So we want to generate this product, right? So I have this polynomial, 3x minus 4, this polynomial, 6x plus 5, and 18x squared, 18x squared minus 9x minus 20 is the product of A and B. So this is how the Chinese remainder theorem is going to work, right? So let's suppose that you've implemented multiplication mod p. So what is A times B if I'm reducing the coefficients mod 5, right? If I'm doing this computation in Z5x. Well, if P1 is 5, now this is confusing. Like the negatives disappear. So there's two ways that we can sort of understand negatives in residue classes. If I tell you like 1 o'clock minus 2 hours, what do you get? You get 1 o'clock, 12 o'clock, 11 o'clock. Is that true? Yeah, so 1 o'clock. 1 minus 2. Okay, so I sort of, that's not the best way. So what is minus 2 on the clock? That means you start at 12 and you go back 2. So 12, 11, 10. Right, so you can always generate the positive version of a negative number in a residue class by just subtracting. So think of it this way. You have numbers mod 7. So those are all the numbers 0 through 6. What would minus 3 mod 7 be? There are two ways to handle this. Realize that 7 mod 7 is 0. So minus 3 plus 7 is the same thing as saying minus 3 plus 0. But minus 3 plus 7 is 4 mod 7. So that's one way of getting from the negative version to the positive version. The other way is to say, if I'm mod 7 and I'm minus 3, just do 7 minus 3. Right? That's the exact same calculation, except I just sort of commuted it. But in any case, so if we take A and we put it into Z5X, 3 mod 5 is 3, minus 4 mod 5 is 1. Right? So that's why we get 3x plus 1 here. Let's take this one mod 5. So 6 becomes 1 mod 5, and 5 becomes 0. So that's why we have 1 here and 0 here. And then we multiply these two polynomials here. You get 3x squared plus 1x plus 0. Right? So this CI here is not the reduction of this product. Right? This column here is what you get if you multiply this one and this one. Right? Because we can't yet do this product yet. Right? Because we're using these products to construct this product. Okay, so you get the product mod 5, right? Then you can do it again, mod 7, and it's just the same procedure, right? So 3 mod 7 is 3, minus 4 mod 7 is 3, 6 mod 7 is 6, and 5 mod 7 is 5. This is what I was talking about before. This is itself mod 7. Right? If I did this mod 13, it would remain itself. Right? So there comes a point when you're in a residue class who has enough numbers to actually represent like the true thing that you are in ZX. Okay, so we have 3x plus 3 and 6x plus 5. That's going to be 18x squared. Mod 7 is 4, right? Because 7, 14, remainder 4. Then you get 15x plus 18x, which is 23x. So I guess you get, is that correct? Help me with my arithmetic. You get 15x and then 18x. So that's 33, I think. And then mod 7, that's 5, right? Because you get 28, remainder 5. And then 15 mod 7 is 1. So again, you're using your polynomial multiplication algorithm mod 7 to take the product of these two things to generate this. And then you can do one more, P3, and you generate the product of those two things here. Now, before we move on, the reason I included this 3 is just to sort of comment on that part of your project about fixing it, right? Fixing something at mod 3. Now, mod 3 is sort of a degenerate case because there's not enough numbers. Like some weird stuff is going to happen. So really, like what we would be satisfied for you to do for those, for doing arithmetic in Z3X is just to isolate what the problem is, right? Search for it, see what the degeneracy is, right? There must be some pattern for the things in ZX that aren't working, right? And I have the impression that it has a lot to do with leading terms disappearing when they shouldn't, right? So if you can't fix it, at least try and deduce the problem, right, the pattern among things happening in Z3. And then I'm fairly certain once you do that, you'll be able to fix it. Okay, so this was like the step 1 of the CRT, right? So let's just ask ourselves, like, how many primes we needed in this case. So what was the height of A? It's 4. What's the height of B? 6. 6 by 4 is 24. This has 2 non-zero terms. This has 2 non-zero terms. So we need to make sure to pick enough primes so that the product of primes is greater than 48. So 7 by 5 is 35. By 3 is certainly in excess of 38. Okay, so these are enough primes to ensure that once we do CRT, or Chinese remainder theorem, on these polynomials, that you've actually constructed the polynomial in ZX. So now the question becomes, Well, you've only told us how to do Chinese remainder on integers. How are we supposed to do this on polynomials? Well, what you're going to have to do is define a function. Well, actually, I don't think you have to define it because I did it here. But in any case, if you can do CRT on pairs, you can certainly do them on lists. Right? So if I give you a list of images, and I give you a list of primes, you should be able to sort of construct the solution. Right? So that is to say, if I tell you that 3 is, what did I do here? Yeah, our secret number is 3 mod 5, 4 mod 7, and 0 mod 3. You should be able to construct that secret number is 18. So what are these? So let's look at this table again and think of what this means. I'm saying I'm searching for this product CI. What do I know about CI? I know that its leading coefficient is 3 mod 5, 4 mod 7, and 0 mod 3. Well, that means I can use CRT to construct what the leading coefficient would be of CI mod 3 times 5 times 7. Does that make sense? Because that's sort of critical to like how this algorithm is working. So I'll say that again. Oh, we have something from the chat. Sorry, why is 3AI in the table again? Oh, I don't know why that's 3. Thank you. Okay, so let's go through this again. I'm saying this is the product of A and B mod 5. And this is the product of A and B mod 7, and this is the product of A and B mod 3. So again, the leading coefficient of the product must be 3 mod 5, 4 mod 7, and 0 mod 3. Right, so that's what this is. So the leading coefficient is going to be 18, because that's the number that was 3 mod 5, 4 mod 7, and 0 mod 3, as returned by the Chinese remainder theorem. Well, I also know that the linear term has coefficient 1 mod 5, coefficient 5 mod 7, and coefficient 0 mod 3. That's what this is. Right? So the linear coefficient is going to be 96 because that is the number which is 1 mod 5, 5 mod 7, and 0 mod 3. What about the constant term? Well, the constant term of the product is 0 mod 5, 1 mod 7, and 1 mod 3. If I give this to CRT, then it will say 85 is the number that is 0 mod 5, 1 mod 7, and 1 mod 3. And thereby we've reconstructed the product, right? The product in mod 5 times 7 times 3 is going to be 18x squared plus 96x plus 85. Now, that's obviously not what this is. So there's one last thing that we have to grapple with. It's the fact that zx has integers, and when we're working mod p, it's because zx will have negatives. And when we're working in mod p, we don't have negatives. So you're going to have to switch to something called the symmetric mod. Now here is the pseudocode for doing it, but it's quite simple. Right? So if I have mod 7, that residue class, I get the numbers 0, 1, 2, 3, 4, 5, and 6. Well, that's one representation. I could also do it another way, where mod 7, I get the numbers minus 3, minus 2, minus 1, 0, 1, 2, 3. It's called the symmetric mod because you get 0 and then like an equivalent amount of numbers greater than 0, an equivalent amount of numbers less than 0. So this isn't actually that hard to create. So if you just have your regular mod, you just have to sort of shift by half the length of the thing you're modding out by when you're greater than half the length. So if you have S mod, so 0 mod 7 is going to be 0, 1 mod 7 is going to be 1, 2 mod 7 is going to be 2, 3 mod 7 is going to be 3, but now 4 is going to be minus 3 mod 7 because 4 is bigger than half of 7. So I would say do the regular mod, so 4 mod 7 is 4, and then you have to sort of shift it, right, by half of 7. Right? So I move that down by, not half of 7, I move that down by 7. Right? So 4, 3, 2, 1, 0, minus 1, minus 2, minus 3. That's 7. Okay, so if you just go ahead and implement this, and we just look at it, right? So S mod, A mod M, is A mod M if A mod m is greater than half of m. Else, it's A mod m minus m. Right, so 0 through 3 here don't get adjusted, and 4 through 6 here get adjusted by just subtracting 7 in the end. Right, so once you generate your coefficients from the Chinese remainder theorem, so these were the ones that we generated, 18, 96, and 85. If we move from the mod to the symmetric mod, you end up recovering those negative coefficients that you were expecting. Right, so 18 S mod 3 by 5 by 7 is just 18. 96 actually goes to minus 9, and 85 actually goes to minus 20. And if you look here, right, those are exactly the coefficients that we were searching for. Yes, sir?
With the implementation, sorry, I'm a little confused on implementation of what we have currently the question for. Would we put the symmetric mod like at the end?
Very, very end. That's the very last thing you do. You just have to do a cleaning step.
So the last step we do when we run the Chinese remainder theorem, we get
Yep, right here. Right. Yes, miss. Pardon me? Because 85 is greater than half of 3 times 5 times 7. Right. Does that make sense? Yeah, if you just go ahead and implement this and just map your coefficients at the end, it's going to work. Right? But anything that's greater than half the length of the modulo will have to be made negative. Like, to just, again, like, keep this mod 7 in your brain. Right? We can either have the numbers 0 through 6, or we can have the numbers minus 3 through 3. Right? Both of those sets are a collection of 7 numbers. And either is fine. It's just that, you know, Z has negatives, so we should recover negatives. Anything else?
Yes, sorry.
Oh, we
Yeah,
have some
I think the line that you select and the example, I think they do not line up. Like the in SMod example, I mean, can you scroll up to the SMod example?
Okay.
So, no, I mean here. So like in the example, if the mod is less than half, then you keep it.
Mm-hmm.
If it's more than half, then you
Shift it.
add the negative here. But I think, yeah, the definition, it does not line up with the example, I think.
Oh, okay.
So like here, if you write that if it's larger than half, then you keep it. But in the example, then if it's larger
If it's
than
larger
half,
than half, then you keep it. Yeah, that's probably. Maybe I have to. Let me think. This is A mod F. If A, oh, yeah.
Yeah, I think you just need to switch
Yeah, I just
the
need to switch them.
last two.
Yeah,
Yeah.
sorry about that. Yep. Yeah, there's going to be some, there's probably mistakes in my pseudocode because it's pseudocode. I can't run it. So like you should trust like my examples more than the pseudocode. I'm just trying to give you a little bit of a hand, but apologies for that one. So that should correct it. Okay, so let's go through like what you actually have to do. So I've simplified this a bit. So you're only going to need to do Chinese remainder theorem on like 2 polynomials, right? The Chinese remainder theorem that I showed you sort of generally worked on like an arbitrary number of things. But if you can do it for 2, you can do it for an arbitrary number of things. So 2 will suffice. So what you want to do here is create a function that takes 2 polynomials and 2 integers, n and m, such that they're co-prime. These aren't going to be primes, right, necessarily, right? Because we're going to have to keep multiplying by more and more primes. And at the end, you're going to have some type of polynomial, which is like a polynomial mod, like 3 times 5 times 7. But they do have to be co-prime for CRT to work. So you give me A mod n and B mod n. And then this is going to construct C mod n times m, such that C is congruent to A mod m and C is congruent to B mod m. Right? And so here's the algorithm. You just set C, which is going to be your solution, to 0. And then for k from the maximum of the degrees of A and B to 0. So what this means, this is just a loop that's going to say calculate the coefficient ck, calculate the coefficient ck minus 1, ck minus 2, ck minus 3, right? So it's saying, so like this could be the leading coefficient of A, this could be the leading coefficient of B, and then you're calculating the leading coefficient of C through Chinese remainder theory. And this isn't recursion, right? This CRT is for polynomials, and this CRT is for integers. So that should be, like, this is not a recursive call. Like, you can call this integer Chinese remainder theorem if you like. So this should be pretty straightforward to implement. Is there any questions about that pseudocode? Okay. So here's how the multiplication works then. You're giving me A and B, and they're both just generic polynomials from Zx, and I'm going to return their product. Okay, so this already presumes that you're able to do multiplication in ZP, right, because of this step. Okay, but this isn't recursion, right? I'm not using Zx multiplication to define Zp, right? You really need to go and write a Zp multiplication algorithm using any of the pseudocode or method that you choose. But this is fine, right? This is not the same multiplication that this is. So I'm just doing sort of exactly what I did in the example. I just got the height of A, got the height of B, calculated the bound that I have to exceed in order to be ensured that I'm returning the coefficients that are correct. I'm starting M at 3 because I'm doing one sort of multiplication outside of the while loop. Right, so this is sort of like your first image. And then you just keep generating new images until this M sort of is in excess of that bound. So this is a little bit cheeky, right? Because like some of these things you're going to have to go implement, but you want to get the next prime that's after the prime that you've last used. You then want to compute the product of the of your polynomials, mod that P. You then want to update C using your Chinese remainder theorem, and then you want to increase like these M's and repeat that. And this is, again, just doing exactly what I showed you in that worked example. So there are already people in the class who have successfully implemented this, so I'm pretty sure this one, you can just, doesn't have bugs, although this had a bug. That 0 used to be a 1. It should have been a 0. So if you're missing your constant coefficients, that's why. Paul, can you comment on if and when the CRT-based multiplication is more efficient than just multiplying two polynomials directly? There are multiple multiplications mod P here to achieve a single multiplication. Well, that's a tough one to get into. I would have to start like talking about like the actual complexity of all of these things, like homomorphism diagrams. But like as soon as the coefficients of the product that you want are in excess of like machine integers, like this has to work better, right? Well, it depends also how you're like dealing with arbitrarily large integers. But it shouldn't take too much effort to actually like see an improvement on like random examples. And it's not really the multiple multiplications mod P here that we need to count. It's like we have to count the total number of multiplications on coefficients generically. And plus, like doing arithmetic mod P is a lot faster than just doing arithmetic on like the generalized integers. No problem. Yeah, I could really flesh this out, but I'd need like a whole lecture to go through, because we'd have to talk about the complexity of integer multiplication and then generic polynomial multiplication, then how fast can we multiply things mod P. But you should see an improvement when you implement this. Okay, so I'm going to talk about PyMod next, but please like ask me your questions about CRT. Right, the one thing that's important is that it's not recursive, right? Because you have to be very mindful about like when you're multiplying two things, where those two things have come from, right? Because you have to remain in that ring. Right? Because I know this was sort of confusing, but if you stare at it, you'll see like this isn't actually a multiplication on polynomials. This is doing an addition of polynomials in one term multiplication. Yes, miss?
Right, this is probably really basic.
I'd love basic questions.
I'm not this far through the process.
Yeah.
So this is like post-task 3, where we're improving just where you just multiply two polynomials and then take it mod P, and that's
No, you do not take the product of two polynomials and then reduce the mod p, right? That would be pointless, right? We need to do polynomial multiplication in mod p and then use those images to lift it to zx. Oh, okay, well, because the other thing would be like a disaster, right? You don't want to like do the multiplication in zx, reduce it, and then reconstruct the thing that you just computed. Yeah, so the first thing that you should do is implement a ZP X multiplication algorithm, which shouldn't be that bad. Any other questions? Like even basic ones, especially basic ones. Yes?
Well, so like, just like a bit clarification on the previous question. So like, what degree of polynomial should we see an improvement? Like just roughly, should we see an improvement?
Well, that's not really the right, like, because you can have a high degree polynomial with like tons of zero terms, like x to 1001 times x, right?
In general, on average, are we thinking of like?
Well, I'm saying like you need to talk about, you need high degree and density, right? You need to make sure there are a lot of non-zero terms present.
As in like, if I put in a polynomial to the power of 5, is it going to be faster, or am I going to have to put a degree 1000 polynomial in to see an improvement?
Again, the degree is the wrong measure, right? Because x to a power of 1000 is quite simple, yet has high degree, right? You need both something of high degree with a lot of non-zero terms, like x to the 1000. Yes, sir?
Suppose it was fully dense.
Suppose it was fully dense. Yeah, I don't know, right? So this is sort of what you're supposed to flesh out in some of your experiments, right? Because I'm not very familiar with like what's in the engine of Julia, right? So this is not really a question I can answer. It depends on like when multiplication on integers shifts from one algorithm to the next, right? So do you have arbitrarily large integers? Like what does big int do? Karatsuba's? Like surely if you start choosing, it's like the coefficients really are the things that matter, right? Like if you want to create a polynomial with really huge coefficients and a lot of them, and you should see definite speed up in those cases, right? So if you have a fully dense like polynomial of degree 200 maybe, its integers are stupidly large, like very close to like 2 to the power of 64, or I guess 2 to the power of 63 if you want negatives, then you should see an improvement there, right? The mod p arithmetic is helping you with the coefficient arithmetic, right? Because when you multiply two huge coefficients, you're going to have to do a lot of like integer arithmetic, which can get expensive when those integers become large. But again, you have to choose polynomials with many non-zero terms. It's not the degree which makes this difficult, right? You can multiply x to the power of 100. You can square that easily, right? That's x to the power of 200. Like sort of the directives of this project is sort of deliberately vague, right? To sort of try and duplicate like what you should expect in the real world. You can't expect to go to a company and to get a very precise specification and pseudocode of exactly what they want you to do, right? It's always going to be vague. You're always trying to sort of guess what the client sort of wants. So getting you to participate in this type of back and forth with the person giving you directives is like is useful, right? Okay, so are there any questions about CRT before I show you how to do PowMod? And again, you can come visit me in my office too if you ever want to like go through an example or something like that. I'd be more than happy to help any of you individually. Okay, so we're going to talk about PowMod again, and just note that like I just went ahead and dumped in pseudocode for you. You can see it's not overly complicated, although I did abstract one step away. So let's go through it all again, and then I'll show you the pseudocode. So remember why we need PowMod. You're going to have to do this computation a lot. And x to the p to the k, that can get really big. So there's a really foolish way of calculating something like this. Okay? You don't want to calculate a to the power of 17 cubed, right? Compute it, and then reduce it. the number that you're going to get from this mod 17 is never going to be larger than 17. Thereby, none of the intermediate calculations need to be greater than 17 either, right? So taking, what is happening? Yeah, letting it do, oh Lord, these Jupyter notebooks are such fun. Yeah, actually computing that huge number was a huge waste of time, right? And if you do it that way, you're going to get overflow. I don't even think this integer is going to be able to fit in a 64-bit register. So what we need to do first is make sure that when we're doing multiplications, that every multiplication that we're doing is reduced mod 17 every time that we do it. So 8 to the 17 cubed, right? You have to do 8 times 8 times 8, 17 cubed times. But if you instead do 8 times 8 mod 17 times 8 mod 17 times 8 mod 17, 17 cubed times, you're really going to control the size of the intermediate calculations that you're doing. Is that a question or a stretch? Stretch. Okay, so that's one of the first things that we want you to do, although I think that's already in the current PAL mod. Okay, the second thing that we want to do is do something called repeated squaring. So this 8 to the 17 cubed, we don't actually want to do 17 cubed many multiplications. That's totally unnecessary. So I'm going to use a smaller example first. We're going to return to the 18 to 17 cubed one later. But consider that, suppose I want to take something to the power of 103. Notice that 103, this is its binary equivalent, so 11001111, which means that 103 is equivalent to the following sum. Right? 64 plus 32 plus 4 plus 2 plus 1. Right? So that's the 64, that's the 32. There's no 16, there's no 8, there's a 4, there's a 2, there's a 1. Right? So you can get these integers just by doing the binary expansion. So I'm just going to say x subscript 2 is the binary representation of x. So notice, instead of doing w and multiplying it against itself 103 times, I can do the following instead. Right? So it's w to the power of 64 times w to the power of 32 times w4 times w squared times w1. If you sum those exponents, you get 103. So let's count how many multiplications we need now. Well, how do I get w squared? Well, I just squared w1. How do I get w to the 4? Well, I just square w squared. How do I get w16? Well, I just square w4. Is that true? Isn't w4 times w4 w8? I think I may be missing one in here. 8s gets, yes, that makes more sense. I square w4, get w8. I square w8, I get w16. I square w16, I get w32. I square w32, I get w64. Right, so to get all of these squares took how many multiplications? Well, 1, 2, 3, 4, 5, 6. And then how many more multiplications do I need to get this? 7, 8, 9, 10. Okay, so I did, instead of 103 multiplications, I can do 10 multiplications, which is like a significant savings. Okay, let's look at this again for this huge number, right? This 8 to the 17 cubed. 17 cubed has this sort of writing as a binary number. So instead of doing 17 cubed many multiplications, how many do I have to do instead? Well, I need 12 multiplications to get all the powers, right? So like 0 squared, 4, 8, 12. And then I need 1, 2, 3, 4, 5 more multiplications to actually sort of get 17 cubed. So that's 17 multiplications rather than 4,913 multiplications. Right? So you just sort of have to stare at this example. It's just when we, instead of multiplying by w, just keep squaring. And then use all of those squares to generate the thing that you need. Okay, so I didn't give you pseudocode last time, but I'll give you pseudocode now. So you can do it like this. If x is an integer, and m is an integer, and m is greater than or equal to 0, because that's the power we're going to be using. This is not going to work on negative powers. And p is a prime. This is what we want to output, x to the power of n mod p. So it's fairly straightforward except for this step. I'm saying get the binary expansion of M. There are various ways of doing this. You can just keep doing like logarithms, remaindering. Like I'm certain Julia is able to convert a number to binary for you. You just have to sort of dig. But suffice to say, get the binary coefficients, right? B naught through BK, where B naught is like the least significant one and BK is like the most significant one. So this is the answer that we're eventually going to return. This is W, the thing that we're going to be squaring. And it's originally equal to X. So for K from 0 to, oops, I can't use K. Let's say I. For I from 0 to K, do if BI is 1, right? That is to say if it has a 1 here, then we do want to include it. So if BI is 1, then multiply my answer by W and then square W and then return the answer. That's more or less it for PowMod. So just implement this and use sort of this as a trace example. Yes, sir. I can't. Can you speak up a bit? Yeah, I'm not sure about the rank ordering of the task, but certainly one of the tasks like is explicitly to do with PowMod. Yeah, and then. Yeah. So PowMod already exists in the project somewhere, but it's only doing the first half of this optimization. And the only reason we gave it to you actually is because we kept getting overflow errors without using it. Right? So we went ahead and made sure that we weren't going to overflow, but it's still left to do this, like the binary powering. And you'll see a pretty significant increase in efficiency, right? Because again, we're doing 12 multiplications instead of 4,000 multiplications. And that's going to be super significant. Okay, so I got like 10 more minutes. If you guys have any questions, even stupid ones, especially basic ones. Okay, I'm sure you if you have a question, 6 other people have the same question. Yeah.
Mine's about my assignment specifically.
If it, like about the Julia?
Well, no, just like problem with my assignment.
Like conceptual or like?
The CRT is 100 times slower than the original multiplication.
Oh, okay, that's a problem. Okay, so we'll have to talk with one of the experts after this. I'm an expert. Like I'm not an expert of the Julia system, right?
This is a Julia problem.
Okay, well I can take a look at it then. Sure, yeah, because it definitely should be faster, right? But Julia does a bunch of funny stuff with optimization, which I'm unfamiliar with. So we may have to bring in one of the experts. Yeah, but there's at least one other student who did it and he claims it's like it's going way faster. So like theoretically, this is sound. So maybe we'll have to find the mistake. Okay, so you guys, is no more questions? Because then I'll give you your 10-minute break as we do the swap over to the next lecture. All right, speak now, forever hold your peace. Okay, go have a 10-minute break.
I think the problem is a lot of us still don't get parts of the assignments.
Okay, let's see.